I like to focus a lot more on gas now. The gas have different topics and they fall under properties of gas law, ideal gas law. In this particular video, I'll focus a lot more on gas law, in particular the Boyle's law. Let's begin. Now, if you look at this container, there are these round spherical molecules, and these are gas molecules. This particular container has the ability to either decrease in volume and increase in volume. So say you decrease in volume, then all the gas molecules are crunched up and they're all mixed in together. So at a very high or large volume, you see these molecules hitting the side of the container, correct? But so is this portion. It's also hitting the side of the container. But which one hits more rapidly or strongly, I should say? You'll probably say that, well, it's the one on the very right. That's going to give you a great amount of hits. And so therefore, that's going to give great amount of pressure. And this is true. Volume decreases. If volume decreases, the pressure that hitting is considered to be that pressure against the wall, that pressure increases. This means that there is an inverse relationship between pressure and volume. So volume goes up, pressure diminishes, but if volume diminishes, pressure goes up. So it's in the opposite direction. In other ways to describe this phenomena is through Boyle's law, and that's PIVI equals PFVF. PI refers to initial pressure, volume refers to VI refers to initial volume, PF refers to final pressure, and VF refers to the final volume. So with this equation, we can calculate what might potentially happen, how much volume has either increased or decreased depending on the pressure, or vice versa. We can find out how much pressure has either increased or decreased depending on what the change in volume might be. I like to demonstrate the Boyle's law through a small demo here. So here I have a syringe, and in this syringe there is marshmallows. There's green, red, and orange marshmallows. Okay, so I'm going to demonstrate Boyle's law like this. I'm going to close this and see what happens if I were to increase the volume. Again, let me try that one more time. I'm going to increase the volume again, all right? Okay. Now, again, I'm not going to touch this piston isn't going to touch the marshmallow. Now I'm going to decrease the volume. One more time, decreasing the volume. All right, so what happened over there? So here I have illustrated a syringe with two marshmallows here. Inside this area are gas molecules. I mean, they're just air molecules all around us. So what happened to the marshmallow? And these are the air molecules, by the way. And what happens to the gas molecules when their volume increased? Well, you can see through the expansion of the marshmallow. Marshmallow is just a representation of how the gas behaves. So there's all these in between the pockets of the marshmallow are oxygen and nitrogen. There are all these gas molecules that are composed in the air. So when it expands, when the whole syringe expands, the marshmallow expands with it too, because the gas molecules inside are also expanding. They're being spread out. However, if you so you can say that volume increased, the pressure decreased. So you don't see there's less hitting of that gas molecules onto the container of the syringe. Now, volume decreased, right? Now there's a greater amount of pressure because now it's really hitting the walls of the container. We can see the volume has decreased not just through the syringe in itself, but also the marshmallow has squished, meaning that all the outside molecules, they're kind of like crunched up together, including the marshmallow. So volume decreased, so pressure increases. There's more hitting of the wall. And this sort of demonstrates Boyle's law. Let's do some problem based on Boyle's law. Here it says, consider a 1.53 liter sample of gaseous SO2 at pressure of 5.6 times 10 to the third Pascal. If pressure is changed to, so pressure is the one that's being changed, and it's giving you a value which is 1.5 times 10 to the 4 Pascal at constant temperature. What will be the new volume of the gas? Okay, so what I like to do is do a simple setup. So initially, the volume was 1.53 liter. Initially, pressure was 5.6 times 10 to the third Pascal. Then it says it changed, the pressure changed. So that's my final pressure, and that changed to 1.5 times 10 to the 4 Pascal. And it's asking for what is the final volume. Okay, so we have this Boyle's law. So let's go ahead and write the Boyle's law. PIVI is equal to PFVF. We're looking for VF. So we want VF by itself. So I will go ahead and divide PF both sides. And that's going to cancel out the PF. And I will be left with VF is equal to PIVI all over PF. Now I can plug in some values here. So my initial pressure is 5.6 times 10 to the third Pascal. Multiply that by volume. So volume initial, 1.53 liters. All over final pressure is 1.5 times 10 to the fourth Pascal. The units of the Pascal can cancel out nicely. And we're left with liters. And that's good because we're looking for the volume, the final volume. Let's calculate this out into the calculator. So I'm going to introduce a parentheses, 5.6 times 10 to the third. Why? Because I like to keep these big, large scientific notation within one set. And that's multiplied by 1.53. And I hit enter. 8568, and then divide that by parentheses 1.5 times 10 to the fourth power. And I get 0.57. And that's my final volume. So let's see if this makes sense. So you see that the pressure, right? Pressure has increased. Pressure has went from 5.6 times 10 to the third to now 1.5 times 10 to the fourth. So there was an increase in pressure. That means since pressure and volume are inversely related, so we should see a decrease in volume. And we see that there was a decrease 1.53 to 0.57. So there was a significant decrease. And so it makes sense how this all plays out. Let's do another one. Aerosol can contains 400 mils of compressed gas at 5.20 atm. When all of the gas is sprayed into a large plastic bag, the bag inflates to the volume of 2.14. What is the pressure of gas in the plastic bag? So again, I like to set up the pressures and the volumes, initial and the final one, before I attack this problem. So why don't you try and setting this up and come back and check the key. So here's the setup I have so far. Now note that over here there's mil, and over here is just liters. So one of these guys, either the liter needs to change into milliliters, or this has to change into liters, either one. The unit needs to be consistent. This is ATM, the pressure. That means my final pressure most likely will be in ATM, unless I change this to something else like torr or Pascal. So there has to be a consistency in the unit when you're solving out the problem. So let's go ahead. I'm used to just converting milliliters into liters, so I'll go ahead and do that by multiplying 1 liter all over 10 to the third milliliter. That will cancel out my liters, and I'm left with 0.400 liters. Okay. Now let's go ahead and set up our Boyle's law. This is final. And go ahead and divide both sides by apologize, V final. Since we have the V final and we want the P final to be by itself. V final cancels out, and so I have PIVI all over VF. And I'm looking for pressure. Let's plug everything in. 5.20 ATM multiplied by 0.400 liter all over 2.14 liters. So liters cancel out, and I will have my pressure in ATM. Let's go ahead and calculate this out. So I have 5.20 times 0.400. That's going to give me 2.08, and divide that by 2.14. That's 0.972, 3 sig figs, right?